Our discussion here will encompass the subject of outdoor building-mounted illumination. When it comes to outdoor lighting, it has a couple of unique properties as compared to indoor lighting. First of all, outdoor lighting is seen by day in a non-functioning manner. So that means that outdoor lighting needs to be sensitive to the surrounding environment, to the architecture, and blend in because it's part of the streetscape, the landscape, if you will. At night, it needs to perform because you need to be able to see by it. So we use the phrase seen by day and seen by at night in order to describe outdoor lighting. Now, an aesthetically appealing building during the day can become even more so when enhanced by lighting at night. Whether it's a contemporary building or one that's more ornate because of it being a more traditional style. In fact, sometimes the traditional style of buildings can be even more dramatically when lit at night because of all of the various features that are part of the overall look. From the outset, for illumination of any building structure to be successful, you need to decide the purpose of your use of lighting. And what we mean by that is you can use lighting to call attention to ornate building features in a more traditionally styled building that has a lot of elements to illuminate, or the building can be very simple in its basic design and use lighting itself as the feature. Sometimes lighting fixtures are the feature, whether they're off or on, whatever the daytime or nighttime environment is, the attention is drawn to the fixture itself. For the most part, though, what our discussion is going to encompass is the type of application where lighting is not seen, but the effect is seen, and the effect enhances the look of the surrounding environment, be it landscape or architecture. So the question that needs to be answered is the fixture itself the focus or the effect the focus? And that becomes the determining factor in how you select luminaires and select the lighting effect that it produces. Now, to effectively make illumination the focus, there's some points to consider. First of all, if light is the feature, what's it going to be? Is it going to be up, down lighting? Will there be different beam spreads involved? Will those beam spreads enhance the structure as far as bringing out features of the structure, or will the lighting itself be the feature? As we see in the upper right-hand corner, as the upper right-hand photograph as an example. Now, to begin with, when we start looking at lighting any type of environment, particularly in the outdoor, there's an element we need to keep in mind called a correlated color temperature, or CCT. Sometimes the term is just color temperature. You may have heard this used before. What that refers to is the appearance of the white light, the basic light itself. In the case of these three examples, 2700K, 3000K, and 4000K, K indicating Kelvin as far as the color temperature, in every instance, these are considered a form of white light, from a warmer form to a cooler form. But you'll notice that the impact that it has on the elements it's illuminating can be very dramatic. On the far left, there's a lot of attention drawn to, if you will, the donut itself because of the warmer tones that are in the light. On the far right, there's more impact given to the blue sprinkles on top of the donuts, again, because of the cooler color temperature of the light itself, the content of the light, the color content of the light. Explain to you what that means in a moment. And this correlated color temperature, or the selection of warmer versus cooler tones, can be very important when it comes to building materials. Selecting the desired color temperature, or CCT, or tuning the white light, can enhance natural materials on the warmer side. On the cooler side, it may not enhance the natural materials, but it may enhance more artificial materials. But it's not just the color of the light itself, or the color temperature of the light itself. There's another element there that's called the CRI, or color rendering index. And this becomes important because color rendering index is exactly what it indicates. It's the ability of a light source to render color properly. Now, to understand the importance of the color temperature and color rendering index of a light source, first we want to understand how we see color. The color temperature of two sources can be the same, but the spectral content of those color sources are different. We see it as white, but the colors that are contained within that source may be vastly different from each other. The reason that's important is that we see color as a reflection of that spectral content of the source. So the colors we see in an object are the object's reflection of the color that's in the source that's shining on it. Becoming a little more specific, and without getting too far into the weeds on this, we can have two sources that are a natural white light, 5000 K color temperature. One may render an apple to its truest red form, the other might not. And the reason for that has to do with the spectral content of the source itself. Though the white light that it produces may be 5000 K, it's getting there with a different blend of colors of the spectrum. Just illustrating what we mean here, if we take a look at a natural white light, daylight as circled above, we see that there's a complete spectrum of colors in there, from blues to yellows, greens, and reds. When we look at an artificial white light, perhaps a cool white LED or a fluorescent, you notice there's a lot of gaps or a lot of missing colors in there. Even though the human eye sees it as white, the color content that's in that the spectral content that's in that white light is not as complete as daylight is. And this becomes a way, this now becomes a way we can understand why we see things in the environment the way we do. If a natural white light that has a full spectral content to it, has all the colors into it, is just like the artificial white light that has all the spectral colors to it, then we have a high color rendering index. The two match each other. Let's use another example that's relatively simple in our day in and day out environment. You go into your room, you look to pick out socks from a drawer, and you have the light turned in your closet. Well, if it's a halogen or an incandescent source, or even if it's a warm white LED source, which are very popular today for interior illuminations, you'll notice on that graph in the upper left-hand side of the screen, there's very little blue content in those sources. Now, they read as white to the eye, but they're not. They don't read as white to the objects they're shining on. This is the reason then that it's difficult to pick out blue and black socks and match them up, because there's very little blue content in a halogen or an incandescent or a warm white LED source that are normally used in interior spaces. You can't see the blue because there's no blue light to shine on the object to reflect back at you. You have to get that sock closer to the window where you have natural daylight coming in, where there's a lot of blue content, in order to see it. And that's what the color rendering index does, is it tells us how close a source between the color temperature and its spectral content mimics sunlight or daylight. The higher the color rendering index, the truer the rendering of the color will be as compared to natural white light. Color temperature and the color rendering becomes very important when it comes to the look of buildings or of projects, and knowing what the materials are, as we said earlier, can come into play here. The upper left-hand photograph, we're looking at a lot of natural materials in the construction of the buildings that we see there, and warmer tones enhance those natural materials. The lower right-hand side, the sunset light that's shining on the building, which tends to slant towards the amber and red tones, again enhances those natural materials. When we think of a noon sky, one that's nice and bright and white, artificial materials come into play and look much better in those environments. If you were to shine a warmer color light on those particular buildings or those structures, they might look a little dirty. They might lose some of their contemporary feel because they don't have the crispness that the white light would impart to them. The use of color has become even more popular since the advent of LEDs as a source. And the reason for that is that LEDs are a very effective way to get color into the lit environment. They're very efficient. LEDs are very efficient at producing color, and they also can be used very effectively to produce kinetic color palettes, if you will. Taking a project like the one we see in the lower right-hand side and using colored LEDs in a color changing matrix allows the look of the project to change, or the look of the environment to change as the evening goes on. The reason for this, we're going to explain here in a moment, has become more evident today than in the past. This is the San Francisco City Hall project that was converted over from metal halide lamps and filters to LED, color LED as a source, very effectively and for a specific purpose. Now, when we look at a metal halide lamp, a 4000 K color temperature metal halide lamp, this is the spectral content within that lamp. You'll notice there's some blues, there's greens, there's ambers, there's reds, but they're not all even, and it's not consistent across the board. There's a lot of gaps in between those spikes. The human eye blends it all together to see white light. But the fact is, these are the colors that are present within that metal halide lamp. This becomes important when we look at color filtering, because filtered metal halide equals a large loss of light, as filters are a subtractive element. The way a color filter works is to take the source light, put a filter in front of it. The filter will then remove all the colors we don't want to see and only pass through the colors we do want to see. So if we take a look, for example, at a rose tint lens, the rose tint lens would have 80% transmittance of all light, because it has very little impact on the overall subtracting of colors from the source. But when we look at that application to a metal halide lamp and see it as the modified chart here, what we notice is, since there's very little red to begin with in that metal halide lamp, there's very little red that comes through, even with the 80% transmittance of the rose tint lens. And those numbers can be directly related to the lumen output of the lamp. So if you had a 40,000 lumen metal halide lamp and put a rose tint lens in front of it, you'd see the equivalent of about 32,000 lumens of light, a loss of 20%. Very dramatic. Another way to see this is with a light source that, or with a color filter that plays a little more in favor of the colors within the source, of the metal halide source. That would be a deep straw color filter. Now, on paper, the deep straw filter cuts even more light out of it. It's only 65% transmittance versus 80% in the rose tint lens. And if you'll notice, everything from about 525 nanometers on the spectral chart on down, going lower than that, or numbers lower than that, it becomes, they're all blocked off. Everything above that, going towards the amber and red tone, are passed through there. But that light has to be present, or that spectral content has to be present in the lamp to begin with. And when we apply that color filter to the metal halide lamp, we notice we end up with about a 60% transmittance, a little more truer portrayal of the deep straw color, because there's more yellow content in the metal halide lamp, but still not complete, because you don't have all of the yellow that's in there as you would in sunlight, for example. And the resultant output is about 40% loss of light, so perhaps 24,000 lumens. This shows that filtering of a metal halide lamp is extremely inefficient when it comes, we look at it as a way of applying color to a project. We have to start off with a lot of light in order to take light out of what we end up with. Now, light is additive. If we take 1 foot candle of light and shine 1 foot candle of light on top of that same spot, we have 2 foot candles. The same thing applies in the way of color. If I have blue light and red light and put the two together, combine the two together to get a purple light, that purple light has a higher lumen content than either the blue or the red, because you've added the two together. This is something that LEDs bring us. And one of the reasons why that's so important becomes apparent when we get into the reds in the color in the spectral content. A medium red filter really only has about 4% transmittance of light. So if we were to look at the metal halide lamp that we started with and see how little red light is already there, or red spectral content is already there, and allow 4% transmittance, the result is 2% transmittance of light from that metal halide lamp. All of those other colors that made up the white light are blocked. They're not allowed to pass through. You have the equivalent from a 400 watt metal halide lamp of about 16 watts of power coming out of there. There's not much that comes out of that lamp. And that's the reason that LEDs can be so effective in color when it comes to illumination of projects. LEDs start off as pure color, and they're additive. With LEDs, there's no light loss. As we said before, you mix the red and the blue together, you end up with more light because they add together. This project, this San Francisco City Hall project, was converted from filtered metal halide to color LEDs. The energy reduction was much greater than a 50% energy reduction as far as its operational costs, and eliminated the cost of filters and replacement labor when it comes to those filters and lamps on the project. And so doing this job in colored LEDs is a very, very viable manner in which to light this project and do so with color because of the properties with solid state illumination, with LED illumination. Another factor to consider when you're looking at using lighting as your source is to consider the patterns that are being used. How are they going to function or work within the project itself? Job that we looked at earlier, the architectural features of the Showcase Cinema project are very minimal at best. There's a little bit of inset in those large panels we see on either side of the entryway so that the uplight and the downlight kind of pick up the edges of those insets. The vertical spaces in between the insets can be down illuminated with white light or up illuminated as they are here with a very narrow colored beam to give it some highlight to it. But when we look at this project overall, imagine taking all of that light away from this building, how plain it would look, how simple it would look. We see a lot of big box stores use this approach today. Costco's, Best Buys, some Target stores, a lot of them use the same featureless type of buildings because they're relatively inexpensive to construct, and then use lighting as a way to enhance the outside look of the building. A little case-in study here is a project that was done down in Florida called Suncoast Medical Plaza. It's on the west coast of Florida. These are renderings by the architect ahead of time about how he wanted the project to look. The image on the left naturally in daylight, the one on the right at the nighttime environment. In fact, we'll enlarge that so you see the renderings, because if you look closely, the lighting fixtures on the building are portrayed as just nothing more than squares, locations for the fixtures to be mounted. But he describes in his rendering the pattern he's looking for as far as the illumination on the building is concerned. Now, let's compare this with the actual result. And these photographs were taken by the architect and sent in to us. This is the real job, photographed just around sunset time. We can see that the intent of the narrow beam uplighting and picking up the features on the edges of the building, and the downlighting giving illumination to the pathways and walkways and more illumination on the building, looks exactly like his rendering. And this is as a result of planning ahead of time the intent of the look and looking for luminaires that would fulfill that intent, or looking for beam patterns that will fulfill that intent. Another thought to point out is when it comes to selecting outdoor or lighting fixtures, there's a couple of things to keep in mind. One of the most important ones is making sure that they can stay clean over the long haul. The two biggest things that can happen to a luminaire, especially in up-facing luminaires, is for water to collect on the lens, and when it dries out, it creates a haze on the lens and cuts down on the light, or it sits on top of the lens in a little recess area and seeps into the fixture and damages the interior components. So the best of outdoor lighting luminaires will put the lens, seal the lens to the faceplate or the lens frame, bond them together in a flush manner. When that lens frame is then applied to the luminaire and screwed down to it, water has no place to stay. It runs right off and out of the way. In fact, if anything, it functions almost like it's self-cleaning lens. Anytime it rains, it cleans that lens off. You have a watertight seal to the body so no water gets inside. There's no place for the water to sit on the lens and intrude inside the luminaire. Another element to effectively make illumination the focus and points to consider has to do with assessing the local codes, particularly the ones that address outdoor lighting, most of which will have dark skies provisions included in them. Now, two of the most fundamental dark skies provisions have to do with color temperature and uplighting codes. Let's deal first with color temperature. As we discussed before, color temperature looks at the total spectrum of light that's involved in the illuminated environment. In the daytime, 5,000 K, we have a lot of blue and some green in that color spectrum. When we work into the warmer tones that we see at night, 2,700 K, 3,000 K, and 4,000 K, we notice that as we move towards the warmer tones from right to left, more and more blue is taken out of the color spectrum. Now, 3,000 K, the center point here of these three illustrations or these three photos, is what is required to meet dark sky provisions. It's a nice medium point, if you will, between 4,000 K or the 2,700 K, because as you go warmer, true, it's friendlier to the nighttime environment. However, warmer color temperatures take away portions of the color spectrum. And as we discussed prior to this, if you remove color from the spectrum when you're in your light source, you don't see those colors in your sight. In some cases, that gets taken to an extreme point for purposes of either wildlife or for other physical considerations. Now, using the example of sea turtles in the Gulf Coast area, the wildlife conservative commissions have mandated a very limited wavelength curve or wavelength of light available to be used in coastal areas, because this wavelength is not seen by sea turtles, for example, in the Gulf Coast. They can't see this amber color. So as a result, when the hatchlings come out and the soil, the sand at night, they don't move towards the streets and roadways or towards the buildings. They move towards the ocean, because starlight or moonlight shining on the ocean will attract their attention in that direction. There is a way to get to this color spectrum using phosphor converted regular LEDs, but if you notice in the graph on the right hand side, there's still a generous amount of other colors that begin to creep their way or work their way into that color spectrum, particularly on the blue and the green end of the spectrum. And this is the portion that we want to eliminate if we don't want turtles to follow that light, if you will. They can see that small amount of blue and that green, and so these are normally not allowed to be used in areas where wildlife is a consideration for the limited wavelength light. Now, when it comes to observatories, for example, in some areas, when it comes to for example, Tucson, or in the Southern California area around Carlsbad, those are areas where there's observatories that need to filter out stray light in order to take their readings. And by having a narrow band of wavelengths that are in the surrounding areas, they can put those filters on those telescopes and remove that light from the work that they're doing. And that's the reason that they get used in these environments. As we stated, uplighting restrictions may come into play, particularly for dark skies provisions. Now, uplighting may be part of your strategy initially. If we take a look at this particular project, all of the horizontal elements of that canopy of that building look very nice as they're illuminated from the bottom up. But if you have uplighting restrictions, this wouldn't be allowed, so the strategy for lighting your project may need to change. You may need to use downlighting only. Now, not that that's bad. We take a look at this particular photograph, the stone, the natural materials in the building are complemented quite nicely by this downlighting approach. However, the horizontal elements on the building are no longer standing out because there's no light catching that edge because you can't have any uplight to it. So that becomes part of the decision you need to make in your strategy of how you're going to light a project. A third area that becomes important is the illumination level control of individual fixtures or groups of fixtures. Now, there's a number of different types of sensors that are used out there. The two most common are what are referred to as passive infrared or microwave sensors. Passive infrared measures the background level versus the level of a body walking through their sensor range, and when it sees a temperature difference to it, it'll trigger the luminaires to either come on, go to full level, or whatever the function is, whatever the trigger is supposed to trigger to. Most of the time it will take a lower light level and trigger it to a higher level, just two set levels, and they call that step dimming. Now, in some instances, it may be the environment may be too warm in the summertime to be able to have passive sensors work properly, so microwave sensors may become the choice. And that way, they can sense the motion of bodies moving through the range of their sensor control. The example on the left is of a device which measures both motion and light levels, and it's programmable in both realms. So you can set this particular device, the lens has been taken off the front so you can see the control points in there, but you can set this particular device so that as it goes from daytime to nighttime, you can select the level that you want the fixtures to trigger to turn on in order to supplement the lighting in that as you approach evening time, and the motion of a body moving through there, the sensitivity of that motion sensing capability can be set, as well as the length of time that the light is turned on in response to that motion. Perhaps you want the light level to step from a lower level to a higher level for 10 minutes. You can set that time on there, or 15 minutes, or whatever it may be, and you can even set the level you want it to go to. So having a programmable device such as this can be done on every luminaire rather than as a group of luminaires. And these are all elements that help you to control the nighttime environment to get the right amount of light on your site, not too much, not too little, and to still be friendly to the environment in the process. There's a lot of shapes and types of fixtures from which to select. Some of them may do exactly what you want. But when it comes to luminaires that we want to enhance or not detract from the architecture, it seems that basic geometric shapes tend to better complement their environment, particularly when they're used in a dual function fashion, uplight and downlight. Note that in these three projects, the attention is on the lighting effect, not the luminaire. The luminaires can be seen, but since they're in harmony with the architecture, they tend to disappear to the viewer. Particularly one to note there is on the lower right-hand side, we see the rectilinear luminaires there on the building, but the building itself is rectilinear, and they almost don't even look like lighting fixtures if it wasn't for the fact that we see the beam patterns coming off of them and creating the illumination effect that's there. Now, while a variety of beam patterns is good, having a bunch of them isn't necessarily better. The better element to consider when it comes to these beam patterns is how smoothly they're created, how continuous they are. Smooth transitions in the patterns will create a clean beam that enhances the appearance of the illuminated surface rather than detracting from it, as can happen when you have a lot of stray light elements within the pattern itself. These other luminaires in the top example will provide some lighting on your building or on whatever your surface is you're trying to illuminate, but the multiple imaging, the striations, tend to take away from the overall look because the pattern is not simple and clean and smooth in transition. In technical terms, in looking at a beam of light, there's two elements there. There's what's called a beam angle and a field angle. Now, there are technical quantifiable elements to define what a beam angle is and what a field angle is, but a simple way to view it is to look at a flashlight. Shine it on a wall, you have that hot spot in the middle, and then you have the kind of halo effect around it. The halo effect, that area, is what's referred to as the field angle. The center beam that's giving you all the intensity is the beam angle. We tend to do a lot better in outdoor lighting when we're working with the beam angle portion of the luminaire or of the optical system. And when we go back and look at these three projects that we saw earlier, that's what we see. We see an even and consistent pattern because the beam angle is what's being emphasized in the patterns that are portrayed. If we take a look at this project in the lower right-hand corner, we're going to compare it to the ones on the top here for a moment. At first, it looks okay, but there's a couple of things that you're going to notice that are different. When I point it out to you, you'll never be able to unsee it again. If we look at the photograph that's in the center of the page, the very top center, you notice those scallops that are on the wall are very even all the way across. The lighting, they all look the same level, and they all look very consistent as far as being nice and smooth transitions. In this bottom photograph on the right, it's rather interesting. You see the striations that are there present from the luminaire. They don't do a terrible job, but they do kind of detract from that main beam that goes all the way down to the ground. And so cleaning that beam up, cleaning those optics up a little bit would have done a lot to enhance the project. But there's another element here that, and I can't explain why it is that this happens. There may be a couple of reasons for it. You have these two columns here that looks like they're at about 50% the light level. Now that may be due to the fact that the luminaires might not be mounted properly, so the beam, because it's so narrow and so tight, isn't fully striking the wall. They might be angled out a little bit or tilted because of an uneven mounting surface. It could be that the optical system inside doesn't have the LED source perfectly centered within the reflector. There might be a number of reasons for it, but this illustrates the importance of selecting luminaires that are well built, that have optical systems that are consistent and that do a good job of creating and exploiting this beam angle for a nice clean presentation. Now, there's a need for all forms of light patterns when it comes to illuminating a project. Some of them, the striations or the little imperfections in the pattern, the field angle area, really doesn't matter. It won't get in the way of the look. And so we see from 10 degrees to what's called a wide flood, which tends to be around 60 degrees. These are conical shapes that give a general downlight illumination. We think of them as down and used in downlighting, it would give us a big circle on the ground. When we think of them up close to the building, they'll give us these various patterns as we see above here on the photographs on the right-hand side. But these are just standard beams with no modifications to them whatsoever. Then you have luminaires that have some optical modifiers built into them so that you clean up that field angle area, take those striations out and deal with just the main beam to have a very clean beam that's illuminating your project. And that's where you get this even, consistent, smooth look, is when the optical modifiers clean up that field angle area. And so there's a need for both type of optics within the selection of your luminaire. Your lighting designer or your lighting consultant or your electrical engineers should be adept at pulling this out, but you as an architect making these aesthetic choices need to be aware that they are available. You don't have to just take the imperfections. There are better quality items out there that you can select to get to the desired effect. And then there's specific patterns for specific purposes. In this case, the primary ones we see are wall washers, a type 2 and a type 4. The type 2 and the type 4 reference optical patterns that are most often seen in site area roadway type of work. They have a definite definition. If we look at this graphic, the type 2 is a rather wide lateral distribution, shorter forward distribution as compared to the type 4, which is a little bit narrower, but it throws light further out in front of it. And that's all the determination of which one to use is all based upon the geometry of the site itself, the characteristics of the site. The wall washer, the first one there, is kind of an interesting creature. Now, we're looking at that graphic is looking at it straight on, not sideways as the type 2 and type 4 are. When we look at this chart that is indicating the power, the lighting distribution power, if you will, of the optic, that egg shape that you see in the center there is what we're looking at when we see the light straight on to the wall. It's nice and even illumination that's the same on either side of center. The other pattern you see, the kind of oblong shape that's a little bit longer and tilted to one side, is indicative of whether the light source is shining straight down, tilted forward, or tilted back in towards the building. Now, tilted out from the building, the pattern you're looking at in that chart is more like the type 2. But a wall wash would take that type 2 and, for lack of a better description, rotate it 180 degrees so that the beam is focusing back on the wall, not out from the wall. And that would give you a stronger illumination on the wall wash, or on the wall to give it a wall wash, and give you a nice even light on that surface as well. All of these patterns together should be available in whatever luminaires you're working with in order to make the proper selection of how to illuminate the beam shapes to illuminate your project. Lighting should be considered as a three-dimensional aesthetic. Except for those rare instances where you may be only looking at a project from a distance, and it might be in a case of perhaps floodlighting of a tall building where you only see the flat surface of the building. Other environments that we look at, and the ones we come across most often in the daily course of our existence, are really three-dimensional. It might be patio areas, it might be atria, it can be anything, but there's elements within that space to illuminate rather than just the wall surfaces themselves. And one of the things that needs to be considered when we're working with this in this three-dimensional concept is that if we're lighting something in a three-dimensional way, people will be transitioning through some of those beams and patterns, and so we need to keep that in mind on how we select luminaires and optional elements that will help control brightness and glare when it comes to the viewer. We look at these large atrium areas, and your typical up-down cylinder is no longer sufficient to do the job. Now you need something that has adjustability to it so that you can pick up points that are further away. And this becomes a very important factor when it comes to flexibility, so that we don't have multiple mounting points, but within the structure of the luminaire, these solid state sources, LED sources, allow us to create fixtures of this type and be very efficient and effective as far as their use. Now, we talked before about the need to consider people in this three-dimensional space. We use the example on the top on this page, a downlight that's static and an uplight that's adjustable to perhaps light elements of a building or a tree in this case. There's probably not too much danger or not too much of a chance that adjustable source will interfere with people's viewing unless there's buildings above that space or a building above that space, floors above that space. The example on the bottom is one that would be far more common as far as needing to take more care that people transitioning through are not subject to brightness or glare that would impede on their ability to see. Here, the bottom fixture is adjustable so that the sculpture that's out there in the landscaped area can be illuminated, but someone can walk down that path and pass right through that beam. And unless that beam is a very controlled and protected or shielded, it could be a debilitating source of light. Now, we've all seen this next slide where someone moves in next door, puts in a floodlight, and they don't pay attention to what's going on off their property site. In this instance, everything above that dotted line is wasted light. It doesn't do anything for the illuminated area. And this is where dark skies societies come into play in order to try and encourage the mitigation of this, to help prevent this wasted light, this light that's called light trespass, from impinging not just on neighboring properties, but just in the environment itself. So what you would need to do is put some type of shielding device on that source in order to control it within the property line. Now, ideally, rather than shielding, it might make sense to select a beam pattern that has these natural properties to it. Then we don't need the shielding. Shields are a way of controlling the light source, but they're not the best way of shaping the source to meet your application. The intent is more to control viewer brightness and glare, not to shape the beam. And when we look at these shields, some of them would need to be so large as to be ungainly looking, a little a little tacky, if you will, if we had to use too many of them on a job, but sometimes they are necessary. Another form of shielding is what's called a hexcel louver. Hexcel louvers are very effective because they can be used inside the luminaire, and they tend to cut off light at angles above 45 degrees from center. Now, if you look at the photo on the right, the photo on the left is pretty much a straight-on view of a hexcel louver. On the right, the louver is tilted, and so towards the back side of the top side of the photograph, which would be the back side of the scene, if you will, you'll notice that it's a little bit darker because you're viewing the cells at a steeper angle. And so there would be more cutoff from the light source coming into a person's view. And that's the purpose of that hexcel louver. The way it functions, just very briefly, is those honeycomb shapes are exactly the same distance across as they are deep. And that's what gives it its 45-degree cutoff characteristic. One of the last areas you want to consider when it comes to outdoor illumination, particularly in reference to buildings themselves, the American Meteorological Society estimates full moonlight on a clear night to be about 0.02 foot candles. Now, that's number doesn't mean anything here or there. It's just to give you a reference. So when you see full moonlight at night, that's about how much light you're seeing is 0.02 foot candles. That's why a lot of jobs that have a 0.1 foot candle or a 1 foot candle minimum, they look bright, because when we look at compared to moonlight, it's a lot more light. Adequate light for reading those considered to be around 10 foot candles, just to give you a reference of the two. And that's not a lot of light. That's just just enough to be able to read without straining, without eye strain. The reason we bring these values up is that across the U.S. and in most countries, developed countries, emergency egress lighting is required to have a 1 foot candle average and a 0.1 foot candle minimum, so that whenever power drops off, a certain amount of illumination or a certain amount of luminaires are controlled by the emergency power systems to create this level of illumination. Now, in older days gone by, using incandescent or HID sources, the power consumption on them was so high that battery packs were not feasible. Most of the time, they would go back to a secondary power source, a generator or what's called an inverter, in order to provide power to these fixtures. It'd be a very expensive proposition to provide emergency illumination, but one necessary for terms of safety. In today's world, more often than not, this can be done with batteries because the LEDs are a much lower draw luminaire. And so the codes that are written require a 1 foot candle average, 0.1 foot candle minimum, and for 90 minutes, that light level needs to hold and may decline as much as 40% to 0.6 foot candle average, 0.06 minimum at the end of 90 minutes. And that's all done with batteries. And this can be incorporated into the luminaires today, either as a supplemental remote device that's close by the luminaires that can be piped into it within 25 feet in most cases, is the distance you can go with a battery pack. Or even more desirable is to build the battery pack into the luminaire or the mounting of the luminaire itself, so that it's an integral system. This way the battery is continually being charged. You have a monitoring device on it that you can push a button to check to make sure that everything is still working, and when power drops off, they immediately come on. It's an install and forget type of device because it's automatically going to work. A little more on this emergency discussion. The human eye has 2 photoreceptors in it, rods and cones. For simplification purposes, rods are color receptors, and we have 3 color receptors in our eyes, red, blue, and green, and cones sense light and motion. Imagine that if you take on your television at home, you turn the color down to 0, you're turning off the rods, and all you're seeing, the cones are functioning there to see the light and the motion. Both receptors work down to about the level of the moonlight. And as we start to drop below the level of moonlight, the rods begin to lose their reception or their color reception or definition, and cones begin to take over, so that on a moonless night with only starlight, it's mainly your cones in your eye that you're seeing with, because you're seeing shapes and motion. You're not really seeing color definition. And this is the primary reason for the 1 foot candle level. The rods and cones are functioning at 1 foot candle. As you drop down from 1 foot candle, the cones become more dominant to a point where you are seeing motion and light shapes in motion. And to facilitate this even more so, that most codes or standards have a contrast level, aside from that 1 foot candle level, says that the brightest point cannot exceed the darkest point by more than 40 to 1. It's called a uniformity, max to min. So that way you don't have bright spots overpowering the dark spots and losing your ability to see. And battery packs in EM systems have lent a huge advantage to being able to cover this adequately and be able to reduce shadowing in situations where it may be a hindrance to egress. And here's what we mean in this illustration. If you note the graphic, we have 2 luminaires located 40 feet apart at a 16-foot mounting height. On the pathway below, the 1 foot candle average and the 0.1 foot candle minimum is met in that 75-foot area. But if you notice between the luminaires or at the extreme edges of the pattern, you may be picking up shadows that might be a little too offensive and might impinge on seeability. So by very simply adding another power point between the luminaires and putting up a fixture that has a battery pack, an battery-controlled emergency pack on it, we can remove the harsh shadowing, improve visibility very, very simply. All we have to do is get power to that midpoint. We don't have to take wiring back to another emergency power source, a second generator or an inverter, just the luminaire itself. And this is already accomplished due to battery packs and the technology in emergency lighting today to enhance the safety and the welfare of people exiting a building in an emergency situation. So to effectively make illumination the focus on any project, particularly one that has a lot of architectural features and aesthetics to highlight, there's a few points that we want to consider. Are we using lighting to enhance, or are we using lighting as a feature on the project? Use a warmer or cooler light, use a warmer or cooler white light, or use color illumination. What is it that you need to do? What are you trying to accomplish as far as what you're lighting? Remember, if you're using a lot of natural materials and natural construction materials, perhaps a warmer white light is more appropriate. Be aware of the colors that you want to enhance in your building. Again, you only see that colors reflected which are part of the light source itself. And if you have warmer tones in the building, you want warmer tones of source. If you have a more contemporary building and a lot of bright colors, you need to have a source illuminating your building or your structure that has those colors in them in order for them to look proper. If lighting will be the feature, make sure that you select cleaner beam patterns so that the less clean beams, the dirtier beams, if you will, don't detract from your project. Consider all the ramifications for emergency lighting and egress lighting. Consider the construction of the luminaire to make sure that it's going to last. A fixture that can last for 5 years on the inside of a building might not last 5 weeks on the outside of a building if it's not built for it. Is your space a 2-dimensional or a 3-dimensional lighting project? If it's treated as a 3-dimensional lighting project, many times the depth of view and the depth of field can be greatly enhanced. Your project is one to be proud of. The aesthetics that are the final result draw attention to the building and to your work for a long period of time. Take the time to develop them properly, to ask the right questions, and to do your outdoor lighting justice, to do your building justice. Concludes our presentation.